Dear students, welcome back to our lecture series for Design of Hydraulic Structures. From the last lecture, that is lecture number 1, we could understand what are the different types of forces acting on a gravity dam. Among the 8 different types of forces acting on a gravity dam, I told you number 1, 2, 3. That is weight of the dam, water pressure and uplift pressure are the most predominant forces that to be considered while doing the stability analysis of dams. In this lecture number 2, we are going to discuss the stability analysis of dams. What are the steps to be considered for doing the stability analysis of a gravity dam. To start with the stability analysis of gravity dams, let's take the example by doing a problem. Already the PDF format of this problem is shared to you. While I am explaining the entire concept of problem, it is advised you to sit with a workbook and a calculator to do the problem simultaneously along with my lecture. So let's start with the problem. Question is, check the stability analysis of gravity dam shown in figure. The figure is given to you. Also, it is given that assume unit weight of masonry equal to 23.5 kilonewton per m cube, unit weight of water as 9.81 kilonewton per m cube, and allowable stress in concrete as 2500 kilonewton per m square. See, this is the figure given to you, and the various levels and dimension of the gravity dam is well explained in this figure. You can see the different levels of the gravity dam. This indicate the presence of a drainage gallery, and you know that the drainage gallery is at a distance of 8 meter from the upstream of the dam. This is the upstream side of the dam and this is the downstream side of the dam. At downstream side, it is inclined at a slope of 2 horizontal to 3 vertical. Using this 2 horizontal to 3 vertical, you can solve this particular angle alpha. Also, for this gravity dam, the top width of the dam is given to you 6 meter and the bottom width of the dam is given to you as 56 meter. To start with the concept of stability analysis, it is very important you have to identify two important points, salient points of a gravity dam, that is heel and toe. See, this is the point called heel of a dam and this is the point toe. So it is very important to identify heel of the dam and toe of the dam. In my further explanation, I will discuss some length and parameters based on this heel and toe of the dam that we can see later on our lecture. Before we go to the details of the problem, it is very important to identify the sign conventions that is being adopted entirely for this stability analysis problem. See, this is the sign convention that we adopt for the problem. You know that we will be dealing with so many different types of forces and also we will be taking the moment of different forces. So the sign convention adopted here as for right force it is positive and for left force it is negative. If it is a downward force, that is positive, then for upward force it will be negative. Again, while taking the moment, you should consider the sign convention. For anti-clockwise moment, the sign convention is positive. Then for the clockwise moment, the sign convention is negative. This is the sign convention that you should keep in mind while doing the entire problem of stability analysis. Now let's start with the problem. At the beginning of the lecture, I told you three different types of forces we will consider for the stability analysis. See, this is the entire tabular column that gives you the types of force, its designation, magnitude, whether it is a horizontal force or vertical force, then lever arm from toe. Lever arm means it is the perpendicular distance between the force and point about which the moment is taken. So from this table or from this parameter, you understand that we take the moment about the point toe. Again, going back, you know that this is the point heel and this is the point toe. For entire problem of stability analysis, we are going to take the moment about toe. That is why here the lever arm from toe is considered, and the last column moment, and moment will be equal to magnitude of force into lever arm distance, and based on the sign convention you have to put sign for this different types of forces and moment. You know the sign convention. Let's start with the first force, that is self weight of the dam. If you see the figure of the gravity dam, you can see that the entire gravity dam structure we can divide it to a rectangular portion and a triangular portion. From the slope given 2 by 3, we can solve the angle, and the angle will be 33.69. You can just take tan alpha, then you will get the angle, that is 33.69. Now coming back to the self weight, the entire gravity dam structure divided to rectangular portion and triangular portion. The rectangular portion weight self weight is marked as W1, and for triangular portion the notation is given as W2. From lecture number 1, you understand that in order to find the self weight, you have to multiply the unit weight of material into the area of the structure. So while taking W1, the area of the rectangular portion will be, the total height of the dam is 84 and this width is 6 meters. So area will be 84 into 6 multiplied by the self weight of the material. In question itself it is given that the self weight of the material is 23.5. So this is W1. Similarly, in order to calculate W2, you know that it is a triangular shape and area will be half into BH. You can see the base and height, that is half into base into height into 23.5 will give you W2. Again, going back to our table, in table you can see that there is a designation W3, and W3 is weight of water column at downstream. From question itself we can identify that this is a problem with tailwater. See, this is the tailwater. If you refer the reduced levels of tailwater, you can see that the tailwater height will be equal to 6 meter. also you know that the downstream portion of the gravity dam is inclined. Whenever there is an inclined portion, whether it is at downstream or at upstream, there will be presence of weight of water. For the time being, here the entire upstream portion of the dam is vertical. So we don't have to take the weight of water at the upstream. But that is not the case at downstream. The downstream is inclined. Whenever there is a portion inclined, whether it is at upstream or downstream, you have to take the self weight of the water at that region also. Here, since the downstream portion is inclined, we have to take the self weight of tailwater also. So the tailwater force, the self weight of the tailwater will be this triangular portion. So that will be half into 4 into 6 into, see, you are finding the self weight of water. So you have to multiply area into unit weight of water. That is why for finding W3, the equation is half into 6 into 4 into 9.81. Now, in order to find the lever arm distance, previously I told you, we are calculating entire moment of this gravity dam about the point tau. So you have to take the lever arm distance from forces to tau. Lever arm distance means it is the perpendicular distance from the line of action of force to the point where you are going to take the moment. So let's take W1, that is self weight of this rectangular portion. You know that self weight will be always acting at centroid. So if it is the centroid, this distance will be 6 by 2, that is 3. So the distance from line of action of W1 to the toe will be this 3 plus 48, that is 51. You go back to our table. See, this is the distance, that is lever arm distance of W1 to toe. Again, you know that the magnitude of W1, this calculation is actually explained previously, and you know that it is a downward force. Since it is a downward force, its magnitude is entered here. According to our sign convention, it is a downward force, so its sign is positive. Similarly, the magnitude of W2 and W3 is written here. You know that W2 is a vertical force and it is a downward force, so the sign is positive. And W3, it is the self weight of water at the downstream side. It is also a downward force since it is a self weight. So that is also written at vertical force column. Since it is a downward force, the sign is given as positive. The lever arm distances of this W1, W2 and W3 is given as 53, 33.33 and 1.33. This 33.33 and 1.33, again going back to our figure, while calculating the lever arm distance of W2 and W3, you know that it's a triangle. W2 is a triangle. Okay, for triangle, its self weight will be acting at B by 3 from base and 2 by 3 from apex. So if you take 2 by 3 of 48 you will get the value 33.33. Similarly, while taking the lever arm distance of say W3, you can calculate its distance to toe also, and the distance will be 1.33. Okay, now we have to fix whether it is clockwise or anti-clockwise moment. Going back to our figure again, this is W1, and W1 we are taking the moment about toe. If you take the moment about toe, W1 will be making anti-clockwise moment. Since it is anti-clockwise moment, the sign is given as, since it is anti-clockwise moment, the sign is given as positive. Similarly, if you take W2, multiply the magnitude of W2 into this lever arm distance, you will get again anti-clockwise moment. According to our sign convention, anti-clockwise moment is positive. Going back to our table, see these two magnitude of moment, these two moments are positive since it is anti-clockwise. Again, W3 is also making anti-clockwise moment with toe, so the sign is positive. These are the first two forces considered: self-weight of the dam and self-weight of the water column. Now let's discuss the third force, that is water pressure. You know that water pressure is the most predominant force against which the gravity dam is designed. Okay, now the water pressure is designated as P1 and P2. Let's see how we can calculate P1 and P2. You can see the figure of water pressure. See, this is the figure of water pressure, and you know that water pressure diagram will be a triangle. The water pressure diagram was explained in lecture number 1, and also the how you can calculate the force due to water is also explained in lecture number 1. So this is the triangular water pressure distribution at upstream. You know that here there is tailwater also, so there will be presence of water pressure at the tail water also, sorry at the downstream end also. From the levels we can understand that capital H equal to 80 meter and small h equal to 6 meter. Entirely in stability analysis, capital H indicate upstream water level and small h indicate downstream water level. Okay, so in order to find P1, that is water pressure or the force due to water at upstream, equal to, I explained you the equation in the last lecture, that is W into h square by 2. See W, where W is the unit weight of water, into h capital H square divided by 2. Similarly, you can calculate the downstream water pressure or the force due to water also, that is W into small h square divided by 2, where small h equal to 6 meter. See, this is P1 and P2. Now you want to calculate the lever arm distance of P1 and P2 with our key point, that is toe. The water pressure will be acting at a height of h by 3 from the base of the triangle. So this is the base of the triangle, and this water pressure will be acting at a height of h by 3. Similarly, at downstream also the water pressure will be acting at a height of small h divided by 3. So you know P1 and this is the perpendicular distance to toe, that is capital H by 3, and while calculating P2, this is your lever arm distance to toe, that is small h by 3. Now again going back to our table, this is P1 and this is P2. P1 equal to and P2 equal to, you know that water pressure is horizontal force, so you have to write in horizontal force column, that is water pressure P1 and P2. According to sign convention, you know that right force is positive and left force is negative. Now taking the lever arm distance, this is capital H by 3 and this is small h by 3. Now you have to take the moment. Moment is equal to force into lever arm from toe. So while taking the moment due to P1 and P2, you see the figure. See, while taking the moment due to P1 about toe, see, this will be the direction of the moment. This will be the direction of the moment. So direction of the moment here is clockwise. According to our sign convention, clockwise moment is negative. While you take the moment due to P2, you can see that moment due to P2 about toe will be anti-clockwise, and our anti-clockwise moment sign convention is positive. Going back to our table, see, moment due to P1 is negative and moment due to P2 is positive. Now let's move to the last force, that is uplift pressure. Before going to uplift pressure, we have to identify which case of uplift pressure is here considered. This is a case of case 3, that is when there is drainage gallery and tailwater. When there is drainage gallery and tailwater, the uplift pressure distribution will be like this. See, at the upstream end, you will be having an intensity W into capital H. At downstream end, it will be W into small h. And at the drainage gallery, the ordinate will be W into small h plus capital H minus small h divided by 3, where W is the unit weight of water. So before going to the calculation of uplift pressure, you have to be very clear with the uplift pressure case, that is case 3 is being applicable here. See, this is the case 3 condition. Here is the drainage gallery, and drainage gallery is situated at a distance of 8 meter, and you know that remaining distance is 48 meter. This is our uplift pressure intensity diagram. By detailing this figure or by calculating this figure, we will get the entire coordinates or entire ordinates of upstream direction, downstream direction, and the ordinate where the drainage gallery is situated. Okay, see, this is a complicated figure, so let's divide the entire figure into a rectangular portion, a triangular portion, a rectangular portion, and again a triangular portion. Means the entire uplift pressure distribution is divided to 4 different areas, and according to each area, the uplift pressure designation is given as U1, U2, U3 and U4. Now it is a calculation of U1, U2, U3 and U4. In order to calculate u1, see, you have to take the area of this rectangle. This coordinate is 300.8, and you know that this distance is 8 meter, that is up to where we have the drainage gallery. Similarly, while you take u2, you have to take the area of this triangle. To find u3, you have to find area of this rectangle, and to find u4, you have to find area of this particular triangle. All the uplift forces are acting towards upward direction. Now let's go back to our table. See, this is u1, u2, u3 and u4. I told you, in order to calculate the magnitude, you have to take the area, and area of u1, u2, u3 and u4, that is being explained here. And you know that it is upward force. Since it is uplift pressure, it will be all u1, u2, u3 and u4 will be acting in the upward direction. Since it is upward direction, according to our sign convention, the upward direction is negative, and the sign convention here is given as negative. Now, in order to calculate the lever arm distance, see, in order to calculate the lever arm distance, every time we calculate the lever arm distance up to toe. So if you take u1, you know that u1 will be acting at the centroid of this particular rectangle. Means the width of the rectangle is 8, so it will be acting 8 by 2, 4. So 4 plus this 48 will be the lever arm distance of u1 to toe. Similarly, you can calculate the lever arm distance of u2, u3 and u4. Let's go back to table. You can check the lever arm distance of u1, u2, u3 and u4. And we are taking the moment about toe. So while taking the moment about toe, see, if you take moment of u1 about toe, it will be clockwise direction. You know that according to our sign convention, clockwise direction is negative. Similarly, if you take the moment of u2, u3 and u4 with toe, the moment direction is clockwise, and clockwise moment sign convention is negative. So the moment due to u1, u2, u3 and u4, you can refer here, it is given as negative, and this moment will be equal to this magnitude of force into lever arm distance. After calculating all the different types of forces, you have to take the arithmetic sum of horizontal forces, arithmetic sum of vertical forces and arithmetic sum of the moment you calculated. While taking the arithmetic sum, you have to consider whether it is positive or negative. So this is the arithmetic sum you are getting. You check with your calculator, you are getting your horizontal sum this value, vertical force sum this value, and arithmetic sum of moment equal to this value. So this is the summary of arithmetic sum of horizontal forces, arithmetic sum of vertical forces and arithmetic sum of moments about toe. Next step is the calculation of distance of resultant of all the forces from toe. That is distance of resultant of all the forces. Resultant of all the forces means in table you have force number 1, 2, 3 and 4. So resultant of all these forces will be acting at a distance from toe, that is being denoted as x bar equal to sum of moments divided by sum of vertical forces. See, sum of moments you have the value here, and the sum of vertical forces you have the value here. You will be getting value 18.06 meter. You can check along with your calculator. Next step is calculation of eccentricity. Before going to the calculation of eccentricity, understand what is eccentricity. Eccentricity is denoted by the letter E. It is the distance of resultant from half the base of the dam. You see, this is the entire base width of the dam denoted by capital B. If you take half the base width, see, this distance will be B by 2. Suppose the resultant of all the forces is acting here. See, capital R is the resultant of all the forces. Then this distance is denoted by eccentricity E. So that you can calculate eccentricity E equal to, you know that it will be B by 2 minus x bar. You know capital B equal to 56 here, sorry, capital B will be equal to 56 here, and you can calculate E using this equation, and you will get the value of E equal to 9.94 meter. The value of E should be less than B by 6. If you calculate B by 6, it will be 9.33. So for all gravity dams, the value of eccentricity should be less than B by 6. But here E is greater than B by 6, so it is not safe. Again, I am adding some more points regarding the eccentricity and the relevance of this B by 6. You understand, suppose this is entire base width of the dam. You know that entire base width of the dam is denoted by capital B. Now I am dividing this entire base width into B by 3, B by 3 and last B by 3. So B by 3 plus B by 3 plus B by 3 will give you entire base width capital B. According to the stability criteria of gravity dam, the resultant of all the forces, here we have the different types of forces, and the resultant of all the forces should lie here. This is the resultant of all the forces. Here means it is the middle third of the base width. See, this is the first third, this is the middle third, and this is the last third. So resultant should lie within the middle third of the gravity dam base width. If you take this B by 3 plus B by 3, it will be B by 6. That is the relevance of B by 6 here. So it is a very important point while the design of a gravity dam is considered. The resultant of all the forces should lie within the middle third of the base width of the gravity dam. Moving to the next calculation, that is maximum vertical stress. The maximum vertical stress can be calculated at 2 points, that is toe and heel. So this is the equation for finding maximum vertical stress at toe and heel. This is the same equation that you studied in your third semester mechanics of solids, finding the principal stress equation. Okay, for tau the equation should be positive, and for heel the equation should be negative. There is the only difference. Sigma v, you know that it is the sum of vertical forces, capital B is the base width, and E is the eccentricity. All the parameters have been calculated in previous steps. You can calculate maximum vertical stress at toe and heel. You can check the calculation. Vertical stress at toe will be equal to 1587 kilonewton per m square. Since it is stress value, unit will be kilonewton per m square, and for heel it will be minus 49.97 kilonewton per m square. Slight variation in this calculation is okay. You'll be getting nearly these values. Moving to next calculation, that is major principal stress, denoted by the letter sigma. Now we are going to calculate the major principal stress at toe. The equation for finding major principal stress at toe is here. There is a term alpha and P dash. You know that this is calculation of major principal stress at point toe. Let's go back to our figure. See, this is the point toe and this is the inclination alpha. So that is the relevance of this particular angle alpha in order to find the major principal stress. Another term is P dash, where P dash is calculated by using equation unit weight of water into small h, that will be equal to 9.81 into 6, where small h is the water level at the downstream direction of the dam. And PV at toe, you know it is previously calculated. You know how to calculate alpha. P dash also calculated. So calculating the major principal stress sigma at toe, you will get value 2267 kilonewton per m square. But you refer question. In your question, the maximum working stress of concrete was given as 2500 kilonewton per m square. Since we obtained value, which value? The major principal stress sigma value here as 2267, which is less than 2500, hence it is safe condition. Similarly, if you calculate sigma at heel, the equation will changes to PV heel sec square alpha minus capital P tan square alpha. Here you have to identify what is alpha and capital P. Alpha actually indicate, see, this is the point heel. If you refer our question, you know that our upstream direction is actually completely vertical. So in effect, there will be no alpha. Just in order to practice, I put the alpha value same as the downstream value. But in your question, if you are having the downstream direction inclined, you have to take that particular angle as alpha in order to calculate sigma at the point heel. Also capital P. In previous step, while calculating sigma of toe, this was small p dash. Here it is capital P, and capital P is unit weight of water into capital H, where capital H is the upstream water level, that is 80 meter here. Just for the practice, I have given this equation. Since alpha is 0, this is actually not applicable here. You can just practice by putting alpha equal to the same value at downstream, that is 33.69. Also, if your PV heel value is negative, for this particular calculation you can neglect the negative value and do the remaining calculation. Next is the calculation of shear stress. Shear stress is denoted by the letter tau 0. Shear stress also you can calculate at toe and heel. You feel the difference between the equation changes at toe and heel. If it is toe, shear stress at toe, this will be PV toe. Since it is toe, the toe means that is the downstream portion. It will be P dash into tan alpha. Similarly, for heel, there will be a minus. Then in bracket, instead of PV toe, here it will be PV heel, and instead of P dash, since heel is at the upstream side, it will be capital P into tan alpha. Here also this alpha at heel indicate if the upstream direction is inclined, that inclination you have to consider as alpha, not as the downstream value. I think you got the value. If you are having any specific doubts in taking these two different angles, you can call me, and I will clear the doubt. And I think now you can do the calculation. Just for practice also, you can do the shear stress at heel also by putting the same value alpha. P dash you can calculate, and you will get the value of shear stress at heel and toe. Now almost we are reaching to the end of the problem. This is stability check. First check is factor of safety against overturning. This can be sigma m positive. You take the sum of all the positive moments and you take the sum of all the negative moments. This is the value of positive moments. This is the value of negative moments. You will get the value 1.58, but it should be greater than 2. Hence, it is not safe against overturning. Next factor is factor of safety against sliding. This is the equation mu into sigma v divided by sigma h, where mu is the sliding friction factor. You can take mu value as 0.7. If it is given in question, you have to take that particular value. Otherwise, you memorize this value and keep and you can take mu value as 0.7 for all the problems. Now you have the sigma v value and you have the sigma h value. You can calculate the factor of safety against sliding. You will get it as 0.965, but it should be greater than 1. Hence it is not against sliding. Just you have to comment whether it is safe or unsafe against these different factors. Now coming to the next factor, that is factor of safety against shear friction factor. This is the equation. An additional term is small q, where small q is the allowable stress in concrete. You can take it as 14 kilogram per centimeter square. Since the entire unit in this problem is kilonewton and meter, you have to convert this kilogram per centimeter square to kilonewton per meter square. This is the conversion, and after conversion you will get 1373.4 kilonewton per m square. Also, you can take the mu value for shear friction factor same as the previous one, that is 0.7. You have the sigma v value with you. You have capital B, that is base width of the dam, and capital sigma of h, sigma of horizontal forces. You substitute all the values and you will get the value as 3.42. It should be greater than 3, hence it is safe against shear friction. So this is the end of our stability analysis problem. In exam point of view, these stability analysis problems are very important. So you have to go through the entire portion of stability analysis very thoroughly. At the end of this week, I am going to give you an advanced assignment or assessment based on our stability analysis problem. I will be giving each one of you the different situation like upstream and downstream water levels, whether there will be drainage gallery, and the distance of drainage gallery will be varying. Similarly, I will be giving each one of you different cases, and you have to work out the stability analysis criteria. The details of that particular problem will be explained later. So hope all of you got the entire concept of this stability analysis of gravity dam. For any doubts, you can call me. While doing the exercise also, you should call me if you are having any doubts. Clarify your doubts and proceed. So thank you all.